Hello, thank you for joining me today. I'm going to be talking about how to implement best practices in terms of I/O performance in HPC, and I'll be demonstrating some of the tools from Ellexus that can help you with that. So I'm going to start off with some slides that outline some best practices using some customer case studies. I'm then going to answer any questions that have come up about general I/O and best practices. I'll then move on to do a demo of our I/O profiling tools and then answer any questions that have come up. Questions should be answered in the questions panel of the webinar application. And so I will pause it at both points in order to look at that. So some of you may have heard about Ellexus already. For those of you who don't, we are the I/O profiling company. We're based in Cambridge in the UK, and we make tools to help you understand the way applications are accessing storage. So obviously I/O profiling is used to help solve performance issues, both in systems and applications. But it's also used to protect shared storage from applications that might be overloading shared resources. And it's also used to look into other issues such as managing application dependencies, making sure you know which files have been accessed, where they're being stored, and so on. And more recently, within the HPC community, I/O profiling is used heavily to manage hybrid cloud resources. So I mentioned very briefly the noisy neighbor problem, and this is a very nice illustration of the kind of issue that you might be looking to solve with I/O profiling and the kind of issues that can arrive if you don't follow I/O best practices. In shared storage systems such as HPC, it's possible for a small number of jobs to overload shared storage by doing too many I/O operations. That could be metadata or it could be reads and writes. And this is an example of one of those applications. The application itself is a third-party tool that's highly optimized. It does a lot of I/O, but it's supposed to. And it's supposed to store lots of its temporary files on /temp, which is local storage. These nodes have got a lot of local storage, and there's absolutely no problem with putting temporary files on there. But this application has been misconfigured to store temporary files on ARM Scratch. So all of that read and write is going over the network unnecessarily and overloading a very expensive Isilon system. And it's slowing down the performance of that Isilon system for all of the users trying to do I/O. So it's a sort of example that's very easy to fix. All they needed to do was to change an environment variable to fix this. And there was a very big win in doing that. We've got two products that I'm going to demonstrate today. The first is Brees, which is a tool for doing detailed I/O profiling. It's not supposed to be run in production because there is a noticeable overhead to collecting the information, but it is very, very detailed. So it will tell you about every single file that's been accessed, the I/O patterns for every process and every file within the application. And you can look at that in a variety of different ways, either through the GUI or via command line APIs for integration into regression testing systems and so on. So the other product that I'll be showing you today is Mistral. Mistral is a live system telemetry tool. It's designed to give you up-to-date information about the I/O patterns of every single job on the system. It doesn't collect as much information as Brees, but as a trade-off is much more lightweight. So it is perfectly possible to run Mistral in production. And that's the tool that you would use to monitor a hybrid cloud system so that you can make decisions about where to put your jobs, whether they're on the right compute and storage resources. And it's also ideal for finding those noisy neighbor applications if they've been submitted by mistake. So why profile I/O? First of all, for detecting dependencies, I'll come back to this again and again. Detecting dependencies is the number one thing that you want to do with IO profiling long before you've started to look at the IO patterns or IO performance of your application. You need to know which files have been accessed, which network locations, and so on. First of all, you need to do this for containerization and migration. I know a lot of people are looking to containerize their applications, usually with Singularity containers in the HPC community. And making sure that you've got the right files to run your application is just number one step to working out whether you've got it in the right place. So again, following on from that is application correctness. Why does an application work for me and not for you? Those are questions that come up all the time and are broadly to do with problems with application correctness. Perhaps you've got the wrong version of Python installed. Perhaps there's a config file that you don't have. All of those things can be very quickly and easily picked up if you look at what is required to run the application. Once you've got to the point where you know your application is correct, then you can look at performance and efficiency. So understanding the resources, making sure you've got the right type of storage for your application, making sure, for example, you've got your temporary files in the right place, profiling IO so that you know how the application is performing over time and how the performance of the storage is affecting that application. And then moving on from profiling, which is more to do with looking at applications in detail, to monitoring IO, which is a much more passive activity for making sure that you understand what's going on in a broader sense, what's normal, kind of whether something has changed in your system. And of course, cost management, everything comes down to how much you're paying for it at the end of the day. So bad IO can come from a number of places. It could come from third-party tools and libraries, particularly legacy code. Compute infrastructure and storage has changed a lot over the last few decades even, and what was good practices 20 years ago is not necessarily good practices now, but there are still applications that assume that storage is fast and local, and that causes a lot of problems. So equally, other misunderstandings about IT infrastructure can cause a problem, and changes in IT infrastructure can cause a problem. So for example, you might have tuned an application to run really well in one environment, but it might run very, very badly in another environment if you're working with a partner organization with a different IT setup. You might upgrade to a new IT infrastructure, bring in a new cluster or move to hybrid cloud, and then suddenly your assumptions don't work anymore. So continuously monitoring and occasionally profiling your applications is pretty important for making sure that you don't run into any of these traps. So I'm just pausing to look at chat messages. I'm not sure they are for me, so I'm going to ignore them. So looking at file and network dependencies, this is a view from one of the products, Brees, and by file and network dependencies, I mean literally which files have been used. So here we're listing the file path, the package that was used to install it, the file name, the file type, and the mount point. This is pretty important. This has been heavily obfuscated, by the way, because it's from Qualcomm, one of our customers. And in fact, dependencies within the semiconductor industry are so important that Qualcomm, like many of our customers in that industry, run Brees as a service where users submit their job to a particular queue and they get back an automated list of dependencies in order to check the correctness of their application for containerization and migration and so on. The next thing you want to look at is how much time you are wasting doing bad IO. So we have developed a methodology that it's very much a first pass. There will be good and bad IO patterns that are specific to each organization or specific to each application, but this is a very good start. So we break down the IO into good, medium, and bad. So medium is things that we're not sure about, we need a bit more context. And good IO are things that are obviously excellent, so contiguous streaming, reads and writes. And bad IO are things that are sometimes bad or always bad. So small reads and writes, often unavoidable given the application. So for example, in the life sciences industry, because of the algorithms, they will always have small reads and writes. But you can definitely avoid opening an unused file. You can definitely avoid failed I/O and 0-byte I/O. So these are all things to minimize. One example of that is an application that the SCFC Hartree Centre recently optimized. So they discovered, I'll show you this profile in more detail later on. They discovered that one of their MPI applications had all of the MPI I/O performed by a single rank, but every single rank on the system was doing the open and close of that file. So you can see that here is we've got one rank selected, and you can see we've got open, close, and an update to the metadata, but nothing in between, no reads and writes. So that was pretty inefficient and pretty easy to fix. So they saw 5 to 10% performance improvement by doing that, with a bigger performance improvement as they scaled to more ranks. So another example of where you can accidentally go wrong with metadata is this is a genome pipeline, and the genome pipeline itself is very highly optimized. And then someone put in a progress bar, and the progress bar looked at the progress of the application by statting how many small files had been created, and knew how many should be created. And of course, by doing this every few seconds, it was massively ramping up the number of metadata and stat calls performed. So this is showing data every 20 seconds. So we're getting up to 1,000 stat calls per second, which is completely unnecessary. There are many better ways to doing progress bar reports without having to create lots of unnecessary load on the metadata server. So again, the sort of thing that's very easy to do when putting together code very quickly, and you won't catch this unless you profile I/O. So I've talked a little bit about monitoring I/O. I'm going to demonstrate our tool Mistral for doing system telemetry. And monitoring I/O really has got to be lightweight if you're going to be doing it all the time. So here I've got an example of what you might want to monitor. I'm showing here metadata per mount point, throughput per mount point, CPU and memory, and that's broken down by, in this view it's actually broken down by node, but normally you'd break that down by job as well. And that's a very good way of just making sure you know what's normal, so you can very, very quickly flag up a noisy neighbor. One of our customers had a problem where users were working on solving workflow problems and accidentally leaving the debug flag on, and that was generating so much extra data. It was really overloading the file system and causing it to fall over. So pretty important to know what's normal and to flag that up before the file system falls over. And I'll just give you one more custom example before I move to the demo. So this is a example of tuning the cancer pipeline at the Sanger Institute. This was a project where the pipeline was already fairly tuned for running in-house, but they do have quite significant compute resources. And for this particular project, they were going to be profiling or mapping 2,000 whole genomes across multiple sites. Not all sites had the access to the compute resources that the Sanger Institute did, so optimizing that pipeline suddenly became a lot more important. So the first thing they did was containerize it for portability. They used Docker to start with, but have now moved over to using Singularity. They tuned it with IO tools, and they also did some IO optimization because it's their own code. They recognize some IO patterns themselves that could be optimized. And then finally, we looked at what resources this new pipeline needed to run, so that other sites could allocate resources appropriately. So the first stage of the optimization was very successful. Runtime was reduced from 32 hours down to 18. So that's a pretty good result. They did that by looking at where the CPU was utilization was low, that those areas where they knew they were IO bound, and they looked at different ways they could optimize that. Most of that involved optimizing small reads and writes. So as I mentioned, genome pipelines usually have lots of small IO, and you can see that in the breakdown here. So the pipeline, that's the top bar is the total number of IO calls, and you can see most of that is reads, and if you can see the yellow, most of that is small reads, so less than 32K. This pipeline is not as bad on small reads though as most, because they've done a lot of work to optimize that. Most genome pipelines look at the less than 4K, dominate on the less than 4K sizes. This one is actually spread 4K to 32K, and they've done a lot of work trading off memory for read size to do that. And it really pays off, because once we ran this across different types of storage on AWS, we found that although the NVMe storage, which we expected to need for this kinds of application, that's generally very IO bound, we found that actually it only gave a 2% improvement across compared with the GP2 storage, although it was 10% more expensive. So actually the default option on AWS was the best. It's still a solid state drive, so still very high performance. So we're still looking at a very IO intensive application. All the other types of storage just didn't have the IOPS to cope with that. But by not requiring NVMe, that's already a noticeable improvement on a very big project. And to look at why, we can look at the breakdown of the IO. So here, both the NVMe and the GP2 both achieved around 7,000 IO operations per second in this in the beginning when the application is IO bound, whereas the provision IOPS and the magnetic disk just could not keep up with that, with around 1K for the provisioned IOPS and 4K for the magnetic disk. We then looked at CPU utilization versus IO operation and read bandwidth. And it looks initially as if the CPU is not being fully utilized here, because we're only using 1 or 2 cores out of the 4 on the machine. However, when we did an experiment to move from an M5 large to a C5 large, which is a much more powerful CPU, and we degraded the memory, we actually found that upgrading the CPU made a significant difference. So this not only ran the pipeline faster, but also we're able to get 90 megabytes per second out of the GP2 storage, as opposed to 70, which is what we got with the slower CPUs. So it just shows as well, even when it looks like you are memory bound or CPU bound or IO bound, you need to tweak all 3 variables to find out. So this profiling took a sort of variety amount of time. Obviously, tuning the pipeline and getting from 32 hours down to 18 took a very, very long time and a lot of effort. So it's only something you want to do if you are going to get the return on investment. So IO profiling initially is about working out where the return on investment is, not necessarily about jumping straight in with both feet and optimizing everything you can see. The next thing we did was to do the sizing experiments, and that was very easy. I think it took 3 days, purely because the pipeline takes quite a long time to run each time, and saving between 10 and 25%, possibly more on the project. That was a pretty good investment there. So in terms of the sort of lessons learned from those particular case studies, obviously containers make it very easy to deploy applications. Optimizing IO can obviously save you money, but you need to understand all the different variables to find the bottleneck. So profiling CPU, memory, IO patterns, and IO performance is really critical. And as a summary of our best practices, I'm going to go back to dependencies. Dependencies are the #1 check. You can find so many problems just by looking at that list of files that have been accessed. So you can look at the wrong libraries, wrong config files, and changes should be checked by a human. You should be running regression tests on your dependencies so that any dependency, any new library that is brought in needs to be checked by a human. You should have 0 tolerance on bad I/O, and you need to test in production because quite often the problems are in the setup scripts or in the final way the application is deployed, not necessarily in the way the application is being designed. And then finally, if you've got time, then you can work out how to do sort of tuning and optimization. So I'm going to move on to the demo, but let's have a look. Are there any questions? I have to pull out the questions panel. So hum amongst yourselves whilst I'm doing that. So here we go. So we've got 2 questions. The first question is, how can I minimize performance hits due to the I/O of others on a shared HPC system over which I have no sysadmin control? Well, unfortunately, if you have no sysadmin control, you should have no control by definition over what others can do on the system. So whilst you can minimize performance hits on your own, that you can minimize the performance impact of your own applications, you can't stop others from doing a denial of service on a shared resource. If you constantly find that this is a problem, then pointing your sysadmin at a solution such as our Mistral product is a good idea, but I'm afraid as a user, there's not a lot you can do to affect other behaviors, the behavior of others. And the next question is very specific. So can you comment on the usefulness of Mistral in a Kubernetes environment using Ceph storage? Yes, so all of our tools work in containers as well as on bare metal. So if you're running Mistral in a Kubernetes environment against Ceph, so Kubernetes is used for a variety of applications. It's used to run and manage microservices as well as containers for HPC. And whereas usually microservices don't do much I/O to be worth getting a specific I/O monitoring solution like Mistral, if you do have a big scientific application that you're running in Kubernetes against Ceph, then definitely having the telemetry in there so that you can see both the performance of the storage from the application's point of view, as well as the impact the application has on the Ceph storage is really important. So I think you'll see when I start the demo a bit more about that. And we also have a question about deep learning applications. So this is, I'm going to answer this question in 2 ways. So we have recently done 2 very different customer engagements. The first was in profiling a deep learning application in order to optimize I/O. And deep learning applications typically have got a very I/O intensive download stage at the beginning and then a very compute intensive stage after that. So we managed to improve the download phase of the application by 4x. We managed to get it down from 12 minutes down to 3. So that was a very worthwhile bit of time spent, partly because this application was going to be scaled to 200,000 instances at a time. So very, very sizable savings there. In terms of using deep learning within an IT infrastructure, that is also something that we've looked at. So you can also use Mistral as the input for a deep learning application in order to reason, forecast, and automatically tune your infrastructure. In a more static environment on-prem, there's limited returns on that. You're better off just looking at the data through a live dashboard and then making your decisions based on that. For a hybrid cloud environment, suddenly the number of choices you get gets more much more intensive. You make far too many decisions for a human in order to really optimize that kind of environment. And so that's where having deep learning as part of your IT infrastructure really comes into its own, assuming you're operating on a big enough scale. So I think, unless we have any other questions, I will move on to the demo. So you should all be able to see a Linux desktop with a command line. I'm going to do a very quick demo of Brees and a very quick demo of Mistral. In order to look at an application with Brees, first of all, you need to trace it, and then you need to look at the results either in the GUI, the command line application, or you need to generate a report. It's not designed to be run in production, so you wait until the trace is finished before you look at the results. In order to have something to see, I'm going to trace Firefox. It's not an HPC application, but everyone knows what Firefox does. That is classic, right, check your demo mistake there. Okay, right, now I have all the right options. I am tracing the application with trace program. That's a script that comes with Brees. I'm putting the results in /temp, and I'm just running Firefox and pointing it at our website. So Firefox opens. I'm going to close that down and load it into Brees to see the results. So I've got Brees running already here. Something seems to have gone wrong there, so I'm gonna, oh, I've loaded in the wrong one. That'll be why. There we go, that looks more like it. So the first thing you see is an IO summary telling you how much time you spent in IO. The runtime of the application was 10 seconds, and it looks like we had about half a second of bad IO and about 1.5 seconds of medium IO. Sync operations, they can be a bad idea and they can take a long time. This is quite a good illustration of that. 1.5 seconds of syncing during a 10-second run is quite a lot of time. You also have a lot of small reads and writes. That's partly because Firefox loads in a load of config files at the beginning. We have some better behaved metadata and a very tiny amount of successful network IO. We'd have more of that if I'd gone to some more websites and not just something that was cached. And as I click through all of these, you can see the list being updated at the bottom. Unsurprisingly, it's telling me that the main Firefox binary was the main process that contributed to that IO. You can see that a bit more easily in the timeline. Firefox actually is an alias for a script that calls base name, file, grep, express before calling the main Firefox binary. And as I'm clicking through each of these, you probably notice it updating on the right. So all of the views on the left are for the main program as a whole, and all of the views on the right are for the particular process that's been selected. So the node view shows you what your program did. So I can see every connection that was made, every file that was opened, including files that failed to open. I can see events over time. So here you can see that actually there was a lot of activity at the beginning, and that tapered off for a bit before I closed the application. So since Firefox is an interactive application, that's not very surprising. And I can also see for this particular process all of the arguments So that was the argument that was passed to the Firefox binary. I can see the system environment, and I can see system libraries, including libraries that failed to load. So this is less to do with checking the I/O and more to do with checking the correctness of an application. We also give you I/O patterns for that particular process. I'm going to switch back to the overview, though, to look at the list of files. So here we have a list of every file that was used by Firefox, and I can see for that file what the I/O patterns were. So I can see reads, small reads, large reads, writes. If I scroll right, you can see metadata and so on. If I open up reads, I can see that the most reads went to proc mount info. For some reason, Firefox reads that over and over again. It wasn't it wasn't the file that took the most time though reading. That was a cache file here. If I sort by full path, just looking at the list of files is a good way of getting to know an application. Here I can see all the dev SHM files, which explains all those syncs that we were seeing. So Firefox uses a lot of shared memory. So that's the list of files. We also show you directories, which is just aggregated file information. We also show you the network. We show you MPI IO. Obviously, Firefox doesn't have any, and we are the IO profiling company, so we show you IO profiling over time. So this is showing reads, writes, bytes, stats, and so on, all broken down by mount point. We also show you IO latency as well, so very important to see that broken down by mount point if you're trying to debug an issue with the file system. So all of the data we collect within our tools is at the application level, so we won't necessarily see problems that are happening further down the stack. However, here you can see a histogram of IO performance, and this has been used quite a bit to diagnose caching issues, because you can see the difference between IO that is on average very slow or IO that is actually very, very fast, but occasionally there's some outlier that's causing the average to degrade. So these are all important things to know about when diagnosing kind of issues further down the line. We have a very good question that's just popped up that I've noticed, which is, do codes need to be recompiled in order to be profiled with our software? No, it doesn't. All of our tools run on code that hasn't been recompiled at all. You don't need the source code. I don't have the source code for Firefox. This is just a completely clean installation. Everything runs in user space, so you don't need to do anything to modify the application. So finally, before I switch to Mistral, I'm going to just very quickly show you what an MPI application looks like in Brees. So Brees will collect a separate trace for each machine that's used in an MPI run. You can aggregate some of the data via the command line, but the GUI doesn't aggregate it. Instead, you'll have a separate trace for each child machine shown here. I've just loaded in the top level trace, and I get the corresponding summary. Unsurprisingly, the IO in this case is a contribution of most of the different MPI runs. If I look at the timeline, you can see all the ranks here. If I click on one of them, this is actually, and then I'll switch to the event view. This is actually the application from SCFC Hartree, which had the problem of lots and lots of opens and closes, MPI opens and closes, and not enough MPI reads and writes. So you can see that here with the MPI open and close periodically. So that was pretty easy to fix. particularly if you look at the MPI run, the MPI stats. So they knew how many times the history file should have been opened. In fact, it was opened 41,000 times, which was some 40 times more than they thought it should be. So that was a big red flag for what could be fixed, and very easy to fix accordingly. So I will now move on to the Mistral demo. So here I've got a very small cluster in order to demonstrate Mistral. It's an LSF cluster with 5 nodes, and I'm going to run a demo which has got 5 different jobs in a loop of 2, so 10 jobs in total. I'll have 2 on each machine. And these are just synthetic benchmarks, so we've got some I/O to look at. All of them are launched onto the Mistral profile queue. Mistral is launched in the same way as Brees via a wrapper, and this profile queue automatically launches the wrapper. So as a user, I don't need to think about how Mistral is run. So it's very easy to sorry, I'm just being distracted by a doorbell when we don't have a doorbell in this office. It's a very odd thing to happen. So on the Mistral profile queue, Mistral is set up to do quite detailed profiling. What's more normal is to have Mistral set up with detailed profiling on one queue, and then so that users can opt into more profiling, but to have more lightweight profiling on the rest of the cluster. So if I kick off that demo, we've now submitted 10 jobs to our Mistral profile queue. All of them are running. They're jobs 1, 4, 3, 50 and onwards. And I am going to run Firefox and take a look at my Grafana dashboard to see what's going on. So I've configured Mistral so that the data gets pushed to an Elasticsearch database. We support different databases, but Elasticsearch is quite an easy one to set up and operate. And then I've got a simple Grafana dashboard that's giving me at the top here those 4 graphs that I introduced earlier. So metadata per mount point, file system, reads and writes per mount point, CPU and memory. This is per job ID now. So you can see, for example, this is the profile of metadata for the home user's mount point for job 14359. But it's much better to see the overview for the whole system. Now, this is set up in a lot of detail. You wouldn't necessarily want to collect this for every job, but you can. I've now got metadata broken down by type, so I can see separate opens, accesses, deletes, and so on. I can see file system seeks, so how random the data is. I can also see writes broken down into small, medium, and large. I've chosen small and medium to be less than 32K and large to be more than 100 meg. And the same for writes. Because you might be trying to spot a noisy neighbor amongst thousands and thousands of jobs, obviously you can set up a table which gives you the top offenders, and that's much better for spotting noisy neighbors on a very busy system. And then finally, here we've got mean latency for metadata and mean latency for reads and writes. So again, just a selection of information that you can see, and you can tune that for what you're trying to achieve. So whether you're trying to do profiling of a large system at scale, or whether you're trying to collect information for forecasting and cost analysis, it's really up to you. So I think we're out of time. I didn't see any other questions come up, and we are out of time. But you can always contact me on the details below if you want to ask any of the questions. Thank you very much for your time.